Hello everyone, I'm Nikita Mahajan, a research scholar from School of Chemistry, University of Hyderabad. And this session we are conducting as a live session, which will be a problem solving session for the NPTEL course named as Ultrafast Laser Spectroscopy. So here we'll be discussing some problems which some few people may have doubt in, and therefore I'll try to solve all of your queries regarding the subject. So first of all, Adrija, you introduce yourself. Hello Adrija, is my voice audible to you?
Yeah, your voice is audible. Hello, I'm Adrija Banerjee. I'm a PhD research scholar from University of Hyderabad. I'm working under the supervision of Dr. Lalita Guru Prasad.
Okay, hi Adrija, it is good to meet you that you are again in the second session.
Yeah,
Yeah, so we'll wait for a time of 2 minutes uh, to just let the people in, because once I start doing the presentation, we'll not be able to join the other people. So I'll wait by around 3 5 if other people join. Yeah, so it seems no one has joined yet. So without any time lag, I'm presenting my screen. Okay. Is this screen visible to you all?
yeah, it is visible.
Okay. So, welcome to the second live session of problem solving for the for the NPTEL course Ultrafast Laser Spectroscopy. So, beginning with this, since we are just coming from week 1 to week 2, there is there are a lot of new things which have come, which we got to know. So uh, I'll just give a brief description of each thing in every question, so that it will be a bit revision of you all. So first of all, the question one is, for a steady state fluorimeter, a good light source would be. Yeah. So first of all, I'll just try to help you with the different terms which are mentioned in the mentioned in this. Question. So first is the steady state fluorimeter. So what is it? So steady state, as you could as we know, whenever we had studied chemical kinetics or something, we had learned about steady state approximation. In order to solve or to find the concentration of some intermediates, so steady state is considered to be a system in which, the system is open, it is not closed, unlike the equilibrium. And the second thing in the steady state is like the rate of the forward process and the rate of the backward process, they work simultaneously, they are equal. And second, it is an open system. So that is what a steady state means. Now fluorimeter refers to the fluorescence spectrophotometer, something which is known to show to calculate or to know the emission intensity. If for any molecule which we discussed in the previous session, that is a fluorophore, something that emits fluorescence. Okay, so again I'll repeat. First of all, steady state, like in order to study the concentration or the kinetics, or the rate constant of how the reaction is proceeding, we just do an approximation. And the second one is fluorimeter. Fluorimeter refers to the spectrophotometer, which helps to measure the fluorescence, or the emission and the fluorescence quantum yield as well. Now, one more thing which I wanted to say is fluorescence refers to the emission from a system. If you consider a system, suppose this sample, so when you incident light on it, it will absorb some amount. Okay. Now, the amount it absorbs, after that only there will be some amount which it emits. Okay. Now the thing is, if you consider, suppose it we give it 100% of light, it absorbs only 80% of light. And apart from that, if you emit the light, means if it emits the light or as photons, then the light would be even more less or lesser. So it will be around for 20 to 30%. Now, what do we want is that the intensity of our emission should be more, because anyways, if you put a sample and you will not get any proper intensity, then what is the sense of doing the entire experiment? So first of all, the need is your intensity of the absorption, sorry, your absorption should be more, and therefore your emission will be more. Because we learned from the earlier session that phi of emission, that is the quantum yield of emission, is equal to I uh, emission upon I absorption. Okay, so anyways, your absorption should be more. uh, okay, so, in all, from all these sources, if you talk about tungsten, we'll come to the point now. If you talk about tungsten, sodium vapor lamp, deuterium lamp, and xenon lamp, a bit introduction I'll give about each. Tungsten filament lamp, it is used to emit, yeah, this lamp emits in the range of visible range. Okay, visible range of light. The second one, sodium vapor lamp. It is known to emit in the range of this UV and visible. Okay. Now the third one is deuterium lamp. It emits in the range of UV, and the fourth one is xenon lamp. So xenon lamp, it emits from UV to visible to IR. Okay. So this lamp has a long range, and second thing, the intensity or the emission intensity for the xenon lamp is very high. So what are the two things we need? The first one is intensity should be high. The second thing is it should emit the long range. Okay, if it emits of such a long range, we need not to use two or more lamps for just one single uh, for one single instrument. So in all, what will be our appropriate answer? That would be the xenon lamp. Okay. Yeah. Hi, Jen. Okay, so we have done only one question till now. And since you are not so late, so I'll just try to repeat this first question solution in in a short uh, period of time. So first of all, our question was, for a steady state fluorimeter, a good light source would be, options were tungsten, sodium vapor lamp, deuterium lamp, and xenon lamp. Now, if you talk about a steady state fluorimeter, so something that works, fluorimeter is something that is used to just calculate the emission, how much emission a fluorophore does. Okay, emission intensity along with the quantum yield. Now, as we had discussed, like as we had known in the earlier as we had known in the earlier lectures of professor, what we got to know is, for a good light source there are certain characteristics which it should possess. So the first one was, it should, sorry, the first one was it should have a high range. Like, it should, suppose you talk about tungsten lamp, so it emits all the visible range of light. If you talk about xenon lamp, it emits from UV to IR. Or if you talk about deuterium lamp, it emits in the UV range. Now if you want to work about a normal if you want to work if you want to select source of light for a spectrophotometer, you will need UV plus visible. That's why in a spectrophotometer we use UV and visible, that is the tungsten and deuterium lamp, their combination. But in the other case of a, for example, if you call about a fluorimeter, we need a source which has a high intensity of light. Now compared to the tungsten and deuterium lamp, the xenon lamp has uh, has higher intensity, and second thing, it has a higher range of this UV to IR. So these are the two main reasons. Sorry, these are the, just a second. So these are the two main reasons why we are selecting this xenon lamp. Yeah. So that's why we are using this xenon lamp. So our answer is xenon lamp because of two reasons. First is intensity, and the second is high range, higher range. That is from UV to IR. Okay. So if you have doubt in this question, I'll just wait for 1 minute. You just think over it, and then we'll proceed to the other question. Yeah, is it okay?
Yeah. It is.
Yeah, so now we'll proceed to the other question. Now, first of all, the question 2 is, a horizontal beam of pulse laser light is reflected by a retroreflector. In order to bring about a delay of 10 femtoseconds in the reflected beam, the retroreflector has to be moved by. Now, this is the case of, like, when you're talking about the time lag which is used to measure the, just a second. Oh, it's not working. Yeah. So we are talking about the pulse laser light. So earlier also in the earlier experiment we had discussed what is a pulse laser light. So pulsed laser light is something like which is not a continuous wave of light. It just starts, it is just for a fraction of second, for a microsecond or a femtosecond. It just starts and then it shuts down. Okay. So this type of pulse laser light we use for time resolution. Now if you want to calculate, when we used to talk about the steady state, uh, a steady state fluorescence spectrophotometer. So we had to calculate this delay of time and the distance. So if you're talking about the pulse laser light, consider this system like, if the light source is coming, like the light is coming from this source, it is coming to this mirror, then it gets reflected through the other mirror. Okay, and then it moves back. Now if I want to this starts from where we had this entire thing starts from where we had kept the sample here, and the pump probe technique which was used to calculate the population of the excited state. Okay, so here what we did was, uh, there like suppose this is our sample, so we had used this pulse pump light to excite the sample. Now suppose this sample all the molecules are in the ground state, so they had reached to the excited state, so this is the excited state. Okay, now what had happened, we had given a perpendicular light, this is called the pump probe light. Okay, so what now if you just give the laser pulse in this direction and the other in this direction, if there is no time lag between the two, we'll get the intensity which is equal, or which is or we'll get the absorbance. Sorry, let's start from the starting. Suppose this is the sample. Okay, now you incident the pulsed pump light to over the sample, all the molecules in the ground state, they reach to the excited state. Okay, now if immediately if you give a pulsed this probe light to this, the absorbance will depend on the concentration of the excited state. Okay, and this absorbance will directly give the intensity of the absorbed light. Got it? Now in this case, what they are talking about, suppose between these two lights you are you want a delay of 10 seconds, so how much should this reflector should be moved? Okay, so for this you will consider this system. Suppose this is the light source, and you are the light is moving from in this direction to this the first mirror. Now it gets reflected, and then it goes through this way again by a second reflection. Now what are they talking about? This is what we are considering here is a normal laser light. So let us consider its speed to be 3 into 10 to the power 8 meter per second. Okay, now the just a second. Okay, I'll just take a clear page where I can explain this. Yeah, so here I can explain. So, first of all, this is our schematics. Got it? Now, here they want a delay of 10 femtoseconds, if I'm right. If any one of you has just read the question properly, just can you tell me if I have written it correct or not?
Yeah, it is correct.
Yeah. So we want a delay of 10 femtoseconds. Now speed of time, what is it? It is 3 into 10 to the power 8 meter per second. Okay, we want that the light should reach 10 femtoseconds late. So how much distance we should move it forward? If we move it, we move it backward, then there will be a phase difference, part difference that will be created, and therefore the light there whatever we want, there will be a time delay. Now, in order to calculate the distance, distance, you know the formula: distance upon time is equals to speed. This is very simple thing. Now, if you want to calculate the distance, that will be speed into time. Okay, now remember here it has, we will just, the time lag includes this and this distance and this also. So, if the speed of light is 3 into 10 to the power 8 meter per second, and time is 10 femtosecond. Now, what is the relation between femtosecond and second? If any one of you knows, please help me with this.
1 femtosecond equals to 10 to the power minus 15 second.
Okay. Do you think you are right?
Maybe.
Yeah. Okay. So actually, this is the relation. So 1 second is equals to 10 to the power 15 femtoseconds. Okay, sorry. Here we'll write 10 to the minus 15. Got it? Now it has converted to seconds. These two will be cancelled. So it will come to be 3 into 10 to the power minus 7. No, just a second. I think it is not 15, it is 14 or 12.
12 is, I think, picosecond.
Yeah, okay. So, yes, we are right then. Okay. So, what will be it will come to be it will come to be 3 into 10 to the power minus 7, or it will be 0.3 into 10 to the power minus 6. I think it is 10 to the power minus 14. Just check it once.
Okay, I will check. I checked, it is showing 10 to the power minus 15 only.
Okay, then. So, then our answer would be, just a second. Now, okay. So it was 3. Yeah. So it will be distance is equals to 3 into 10 to the power 8 into meter per second. And the other thing would be 10 to the power minus 15, and into time we forgot to do, that is 10. Okay, and this is also femtoseconds. And okay, 10 femtoseconds, and we have converted it to second. Got it? So this is 10 into 10 to the power minus 15. So if you just do the total, it will be 30 into 10 to the power minus 7, and it will be 3 into 10 to the power minus 6. So it will be 3 micrometer. So this is it. Now, since it has come to be 3 micrometer, and what initially I was talking about is it has to travel this entire distance. Okay. So that's why we'll just do its half, and therefore we have to move it by 1.5 micrometer only apart. Like if we move it a bit backwards, the phase difference or the delay which we want of 10 femtoseconds will be achieved. So, if you have any doubt in this question, just ask me. Yeah, so now we'll move on to the next question. In their electronically excited states, generally, organic acids become stronger and organic bases become weaker. And organic acids become weaker and organic bases become stronger. The third is both organic acids and bases become weaker, and both organic acids and bases. Okay, sorry, just a second. The become stronger. Yeah. So now it is correct. So what is the correct option? Now, what is the electronically excited state? So, I'll go to the description page. Now, this is your system. Okay, yeah. This is your ground state, and this is your excited state. Now, if I want to consider this system like for any molecule, so I'll just take the example of molecule phenol. So this is it. Okay. Now, what we have done is, this is the solution, and we have excited it. So, what does the excitation means? The range in which it absorbs, we'll just illuminate it with that range of light, and therefore it is called to be an excited state. Now, suppose this is the population of the ground state. Now it has reached to some excited state immediately. What will happen in this state? If we talk about this, the what will be the acidity of this? It can be in its excited state, or suppose if it will work as an acid, it will just form a phenoxide ion, which is given as O minus plus H plus. So this will be its representation. Now, why will it be more or less, however how much acidic it is? Why will it be acidic? The reason for this will be because this electron pair which it has, it will get delocalized in this molecule. Okay. So how it will get delocalized? If we talk about benzene, it always has 3 pi and 3, sorry, 3 bonding and 3 anti-bonding molecular orbitals. Now, as we know, these are the filled ones. These bonding orbitals are the filled ones. But still it has 3 vacant orbitals that are anti-bonding, where it can accommodate this electron pair. And that is the reason why this phenoxide ion is stable. Okay. Similar to this, we when you talk about any organic acid, because of this delocalization, or you can say this excited state thing, the organic acid or any organic base, its acidity will increase in electronically excited state. Okay. Now, if you want, if we just take an example uh, of any organic base, if you want it to be in detail, or else if you understood this thing, we'll just proceed to the other question.
For organic bases, can you explain?
Yeah, okay. Suppose you take an example of any organic base. For any organic acid or base, you consider the entire principle would be the same. That is based on the photoacidity thing. Okay. Now, there is an example which I think sir would have explained in the lectures. That was, if you talk about a system like, suppose it has uh, alpha naphthol. Okay, sorry, a beta naphthol. Okay. Now, this beta naphthol, if you or an acetic acid. Now, just take example of two acetic acids or a acidic medium which has some pH range of 3. Now, if I take acetic acid as an example in this solution, do you think at pH 3 the acetic acid will be ionized, or the beta naphthol? No, it will not be ionized. Okay, it will still be in the beta naphthol state. But if you just illuminate it with light or something, light of a particular range, then you will see that along with the beta naphthol there will be, you will see, like suppose this is the absorption of beta naphthol, you will see some absorption that will be of the other like beta naphthol, the counter the anion part. Okay. Now similar to this, if I take example of a base, suppose it is uh, triethylamine, in that case also no, okay, triethylamine, then okay, I'll I think there is some doubt in this question. I'll try to solve it in the next session. Adrija, is it okay with you?
Yeah, it's okay.
Now question 4. A TCSPC experiment is carried out with a TAC range of 50 nanoseconds and the MCA gain of 8,000 channels. The temporal resolution of the experiment in picosecond per channel will be. Now, the full form of TCSPC is time correlated single photon counting. Okay. In the TCSPC experiment, the TAC range. Now, what is TAC? Can you tell me, Adrija?
50 nanosecond.
No, what is the full form of TAC?
Mm, I do not know.
Okay, so TAC stands for time to amplitude conversion. And MCA stands for, do you know this?
Mhm.
Okay, multi channel analyzer. Yeah. So basically, for this, I have just given the schematics of the experiment. So initially, if you talk, this is your laser source, and DL stands for the diode laser, which is used now as the source gives a short laser pulse. This laser pulse moved to the polarizer, and then from the polarizer first, this polarized light moves to the sample chamber. Okay. Now this short laser pulse, which is given by the diode laser, it is like in the form of elliptical, which has the component of the right and left circularly polarized, right and left electrical component, which are not equal in intensity, and that's why it is the in the form of elliptical. Now when it passes through the polarizer, we'll get a linearly polarized light, which will then pass through the sample chamber. Now from there it will pass through the second polarizer, and from this second polarizer it will pass to the monochromator. Now, what does this polarizer do? This polarizer further polarizes the light and passes through this to the monochromator. And this monochromator then emits a particular range of light which goes to the CFD. But now, in this entire setup, this is the emitted light or the transmitted light from the sample chamber, which moves to the CFD, which is the constant fraction discriminator. And from this constant fraction discriminator, through this time lag, like there is some light wave, some emitted light which is passed, which is in the form of, you can say, it generates a voltage. Okay, and which which is responsible for this charging of the capacitor at this start. And again, in the system, from the diode laser, again a synchronous electrical signal that comes from the CFD, the constant fraction discriminator, again passes and then reaches the stop. Now, this charging of the capacitor here in the tag continues from this start to the stop. Now, since there is some time lag between this pulse and this pulse, between that time lag only this capacitor is charged. Now, how does it discharge? There is a resistor here through which it discharges, and when it discharges, it produces a voltage. Okay, and this voltage is directly proportional to the time lag, that is delta t, or and the second thing is directly proportional to the intensity. So this is the entire setup of this TCSPC instrument. Now what we are given is a TCSPC experiment. Okay, there are few things left. The first one, this DL is a light source. This entire involves the sample chamber, monochromator, and this thing. And from this starts the detector setup. Okay, and from the detector, this signal moves to the computer, where this multi-channel analyzer, it is used to just transform that entire signal into the one which we can see and study. Okay, so there are what does this stack range mean? Stack range means time to amplitude conversion, which like the time for which it will record this signal, or the time for which it will wait for this signal from this electrical signal to come. Okay, so this will be that tack range. Sorry, this will be that tack range. So it will wait for 50 nanoseconds for the signal from this stop to come. Okay, because this entire process will stop only when you just stop it from here. Okay, because it will get started when this light will enter through the CFD to this. Now, yeah, so the resolution more or less, how does it depend? The more the number of channels you are using for individual nanoseconds, the more will be the resolution. Okay, now if suppose the time tack range is 50 nanoseconds, and you have 8,000 channels. So for each nanosecond of signal, for each nanosecond, how many channels or for like will work. So that will just decide how much the resolution is. Okay. So suppose in order to find this resolution, will be we'll calculate as 50 nanoseconds divided by 8,000. Okay, this is very simple. So here it comes. Okay, just a second. Yeah, and we have to give the answer in picosecond per channel. So first this nanosecond will convert to picosecond, so it will be in 10 to the power 3 order. So again these two will be cancelled and only 110 will be left with us. So that will be 50 upon 8. And if you people can calculate this ta- what 50 divided by 8, just calculate it in a second. Just try to calculate.
It is coming 6.25.
Okay, yeah, so this is the answer. This is our answer, that is 6.28. Okay, now actually, now suppose I give you the answer of around sorry, I give you the question, if the time is 100 nanoseconds and you have 10,000 channels, say. Just calculate the answer. Just a second. Yeah.
It will be like 10 picosecond per channel.
Now see, it is for earlier it was 6.28 picosecond per channel, and now you have calculated it as how much?
10 picosecond per channel.
I think it is it correct? Just check once. 100 nanoseconds into 10 to the power 3 upon 10 to the power 4. So this will be 10 picoseconds, right?
Yeah.
Okay. So it will be 10 picoseconds per channel. Okay. Now our problem is solved. Now just guess from if you have just followed sir's protocol, or if you have slight observation, or just tell me in which case the resolution will be more.
In the second case, I think.
Okay. 6 point okay, first one was 6.28. Are you sure it was
Yeah.
6.28?
6.25.
Okay. Yeah, so 6.25. Okay. So the answer would be yes. In the second case, the resolution will be more, but like sometimes resolution is not the only thing. Like more resolution is also not better, because it will take more time for that experiment to occur. Okay, so for that you need like you need an optimum resolution to be decided. Okay, now, if you have any doubt in this question, just ask me. Just a second. If you have any doubt, just please ask.
No doubt.
Yeah, okay. So we'll continue with the next question. The constant fraction discriminators work with TTL pulses. Okay. The second is filter out the fluorescence light from excitation light, generate zero crossing pulses, and provide precise tuning information. So, what are these constant fraction discriminators? Constant fraction discriminators we had studied in this scene. So, constant fraction discriminators are something which just prevent just generate zero crossing pulses, so that there is no, like suppose this is your pulse from the laser source. It is divided into two parts. The like this one from this and one from into this, and then when you just join it, like they'll be in the form of this. There will be zero crossing pulse. Okay, so the answer would be generate zero crossing pulses. Now, question number 6. In the in the TCS-PC experiment, the pulse pile effect is minimized by recording data at only 1 to 2% excitation rates using reverse mode. The third option is maintaining maximum possible repetition rate, and the third is use MCP PMT. Now, uh, if you uh, just a second. Yeah, so we have come to question number 6. In the TCS-PC experiment, the pulse pile effect is minimized by recording data at only 1 to 2% excitation rates, using reverse mode, maintaining maximum possible repetition rate, and use of MCP PMT. So, the pulse pile effect refers to, suppose you have given the pulse of which repeats itself in every 10 microseconds. Okay. And like if it gets repeated at such a faster rate, what happens immediately? If there is a system, you just excite it with pulse, it reaches to some excited state, and immediately you like there will be a second pulse coming back. And so like there will be less resolution, you will not get the precise reading what you want. So this is something called the pulse pile effect. So in order to minimize it, you should always prefer to like record the data at only 1 to 2% of the excitation rates. Okay. And now we'll proceed to the next question. Question number 7. The charging and discharging of a capacitor is of central importance in PMT, CFD, TAC, and MCA. So, few of these options, CFD, TAG, and MCA, these are something which we had learned in the early TCS PC schematics. And if I'll just give a slight detail about each one again. So, yeah, so just a second. Yeah, so earlier we had discussed this. I'll just try to give it a short experiment and just tell me where had we discussed the thing about capacitor in this diagram.
in TSC.
Yeah. So what was this TSC doing?
Like the capacitor was being charged and whatever was being discharged, that voltage passed through MCA.
Yeah. Okay. Now how was like if you're talking about CFD, what does it stand for? CFD stands for constant fraction discriminator. So what does it help in? Constant fraction discriminator, it produces zero crossing like pulses. Okay. Like if you do not get peaks which are like suppose, which is something this, and okay, this is like they are crossing each other, so we do not these such sort of discrepancies which uh, hinder the experiment. The CFD just prevents those. So, what was the thing happening earlier? The light which was coming, the light signal which was coming from here, it used to pass through the CFD, and would you this would generate a voltage. Okay, sorry, this would generate an electric signal which would just charge the which, and there would be a capacitor here, and it would start charging. Okay. And how would it start discharging? Sorry, if it starts charging, when will the charging stop? The charging will stop if there when the synchronous signal, that electrical signal that comes from this diode laser, this electrical signal, when it comes here with a delay of some time seconds, it will reach sorry, it will come here and just stop this process of charging of the capacitor. Now this is the process of charging. Okay. At this point, when you will get a stop signal, the charging will entirely stop. Now how does this discharge, this capacitor discharge? So how does it happen? There will be a resistor here. Okay. And what does this resistor, when the current passes or when this particular voltage passes through this, the capacitor will be discharged. Okay, and this thing will generate a voltage which will go to this multi channel analyzer, and therefore you will get something like this. Okay, and this will be in terms of intensity or the log of something to y. Okay, so if you go to this question, the charging and discharging of the capacitor is of central importance in PMT. PMT, what is the full form? Can you just guess?
Photomultiplier tube,
Yeah. So what is it? Where is it used?
spectrophotometer,
Yeah, it is used in the detectors. Okay. The second thing is CFD, constant fraction discriminator, TAC, and MCA. So, based on the explanation, what do you think will be the right answer?
tack.
Yeah, so option number C, TAC would be the right answer. Okay, if you have any doubt in this question, just feel free to ask, or else we'll proceed to the next question. Okay, so we'll move to the next question. Reduced chi-square and weighted residuals are parameters of goodness of fit, are completely unrelated to each other, should both be considered while data fitting, and does not depend on the range of fitting. Now let me tell you, in this question more than one answers can be right. So you just I'll just tell you the details. So reduced chi-square value. Okay, sorry. Yeah, so reduce chi-square value, which we had which was discussed in the lectures. This just tells about how much correct our data is. Okay, so or you like you can say directly, it is the one of the parameters for goodness of fit, how fit our data is. So if it's we talk about its value is somewhere very close to 1. Okay, and it should not be very much greater than 1 also. And the other thing, weighted residual. So when you talk about the distribution, solving the data and in the different parameters, so these two are the parameters which are the parameters for goodness of fit of the data. And when you just try for the data fitting, these both of these things should be considered while data fitting. Okay, so suppose if you have a spectra which has come in the scale of, suppose you have a single exponential fluorescence decay. So suppose it is in like this way, where this is the log of the intensity, and on this y-axis you have the some x-axis you have time as a component. So these each val suppose if you plot it, in case your data is a single exponential decay, then you will get a straight line. Okay, now if it is a multi exponential fluorescence decay, this straight line you won't get. And how you will just check whether your fitting is good or not in the software, your by checking what is the value of your chi-square. So in all these the two values, weighted residuals and the reduced chi-square, these two are the values which you should consider, which are the parameters for goodness of it, and which you should consider while data fitting. Okay, now we'll come to question 9. the value of reduced chi-square should be. Okay, so when you talk about the chi-square, again I'll just try to repeat it. um, what is chi-square? So chi-square is the value, is the parameter which we consider when we are fitting the data, and when we are just trying to find uh, our lifetime, in the lifetime, or the TCS-PC experiment. So this value of chi-square, its value should be close to 1, and if it is less than or more than 1 or equal to 1, then it is not considered to be relevant. Okay, and if in your data you are getting some value in these terms, you try to reduce the suppose if you're trying to fit the data to three orders, and you get the value that is sort of 1.38. Okay, and like this is, you can say not very much close, this is very much greater than 1. So you will just try to reduce the range, or you will go to a lower exponential value, that is 2. And if you get the value to be 1.26, then still you will go to 1 and try to, like, then you will try if you get somewhere the value between 1.06 to 1.05. Okay, now still if uh, going to 1, you don't get the exact value of 1, somewhere near to 1, and you get it around 0.98, then again you have to change the range or something, play with all these factors to get this value of chi-square value, which will be in the range of 1 point something. Okay, and if you see in the experiment how you will get it, suppose this is the line. Okay, this is the decay. Okay, so you will get it something starting from here and going through this. I just hope you are able to understand this. Like, the fitting on the single line will not be good, so for that purpose only you have to change these orders. Okay, change the range, try to just change it, and so that you get a good fitting. So these are all the things when you just conduct the entire experiment and are working for the data fitting and the lifetime and the quantum yield things in the experiment. Now if you have any doubt regarding this, just ask me.
No doubt.
Yeah, okay. Yeah, so we'll proceed to the next question. A fluorescence decay is fit to a tri-exponential function with the following parameters: a1, tau 1, a2, tau 2, and a3, tau 3. These are given. Now, the order of relative contribution of the components to steady state intensity will be. Okay. So, first of all, what is this fluorescence decay? Okay. So, suppose this is a, we'll go to a blank page. Suppose this is a system you have excited with some range of light. Okay, now it has gone through this some state, and then it is radiating. Now in this, suppose this decay has happened, and there are like three components. Now how do we study this? The intensity as a function of, intensity as a function of sorry intensity as a function of time, it depends on the intensity of the excited state at time 0. multiplied by e to the power ai, sorry, summation of ai and e to the power minus t by tau. Okay, and it will be the integration of this from 0 to infinity. Now why do we consider the infinity lifetime? Suppose this is our log of intensity versus its time scale. So how many parts do we divide this time? So there can be number of divisions. Now you can take infinite divisions in this. That's why we have taken 0 to tau, although in practical life there will be some finite time divisions. So each one it, what is it, intensity of the excited state at time t. I naught will be the intensity of excited state at time 0. AI will be the amplitude of each each time depend. Sorry, what is that? Each function, and the e to the power minus t. So t will be the time and tau will be the lifetime. Now this tau lifetime, what is it? Tau lifetime for a radiative process is the average time spent by any molecule in excited state. Okay. Now and also this tau, it has some relation with the quantum yield and the rate constant of rate constant of the radiative emission. What is it? Suppose this is the quantum yield is equals to rate constant into uh, the average lifetime. Okay, the rate constant of the radiative process into the lifetime. Now if you this equation, why do we, when you resolve it or when you just solve the data using this reconvolution technique, then you use this equation, you integrate all the factors, and then you will get the intensity at any time t. Suppose in this graph, this is the log of intensity and these are the times. So at for each time, what is the intensity of each state that you will get? Okay, and slowly it will reach to zero, means slowly the excited state population, since it is a factor of time, so slowly it will go to a zero, like you will get no intensity. Now what is it? Each one, the amplitude and the time. So when you just see this equation, you will get that there are two factors. There are two. eh, yeah. So yeah, so these two options, AI and tau, these are the two parameters on which the intensity depends. Okay, so here in our question, what was asked? First of all, it was asked that it is a tri-exponential function PQR, okay, and the fluorescence decay is to fit to these functions and the relative contribution. Now, I give you a random question first, uh, and then I'll just give you this question and just ask you whether you got or not. Suppose if the amplitude, the value of it would be say 0.2 for say A and B. Okay, its amplitude is 0.2 and the other and the time lifetime of it would be say 1 nanoseconds. Okay. And for the second one b function, it would be zero point 0.3, and the lifetime will be 5 nanoseconds. Now you just tell me what will be the contribution to the this intensity, because I have already written the relation. So, what will be the relative contribution of A and B, and whose relative contribution will be more? Because see, from the equation, the value of I naught will be fixed. Okay. Okay. Now, what are the value of T, or also you can say it will be fixed. So what are the two things that are working here? The first one is ai and the second one is tau. So these two things are working and or the changing, and therefore the intensity will depend on these two factors only. Yeah. So for the first one,
Can you please repeat? I got disconnected.
oh, okay. Yeah. So we were talking about the fluorescence decay is fit to a tri-exponential function with the parameters a1 and tau 1, a2 and tau 2, and a3 and tau 3 for the three functions. Okay, you have got the value of a1 and tau 1. Now since you do not know the value of a, what is a and tau, I'll tell you that a1 is the amplitude that depends on the population of the excited state, and tau 1, what is it? It is the lifetime. And then I had explained this also, like in order in the TCS PC experiment, when you are talking about for the how to solve the data, how to interpret it, we use this thing. So wait, I'll write it again because that is not looking proper. Yeah, so for any intensity at time t, the it will be given by the expression I at 0. What is this I at 0? I at intensity at O is the intensity of the excited state at time 0. Okay. What is IT? IT is intensity of excited state at time t. And then again in this equation, there are few other factors which are incorporated. The first one is multiplied by, yeah, okay, summation of a summation of ai integration 0 to 0 to infinity e to the power minus t by tau. Okay. Now suppose you get this signal, okay, where this is log of intensity and this is the time scale. So you will get something like this. Okay, got it? Now See, why I have taken 0 to infinity? Why? Because this entire time scale I can divide it into infinite time, small time intervals. Okay. Now it depends on me in how much intervals I do divide them. Okay, they can be in a finite range, or normally if you say they are always in the finite range, but for calculation purposes we have taken them to 0 to infinity. The second thing is AI. So what is AI? AI is the amplitude of the ith, say ith time scale. So amplitude, on what factors does it depend? Amplitude depends on the population of the excited state. Okay. And what is tau? Tau is the lifetime, average lifetime. We can say average time spent by any molecule in the excited state. So this is written excited if it is not clear. Now, suppose now that thing depends on the molecule itself. It can be in the range of 5 nanoseconds to 50 nanoseconds or more than that. Okay. Now, here they have asked that the fluorescence decay is fit to a tri-exponential function with the following parameters: a1 tau 1, a2 tau 2, and a3 tau 3. The values of each one is given. The relative contribution to the steady state intensity is. Now here the intensity, the IT will depend on I naught, A1, AI, and tau. Okay. Now this T is also fixed. Same. So, how are these factors affecting? If I we talk about I naught, so I naught. Okay, yeah. So just a second, something happened. Yeah, yeah. So we'll go to the next slide. I think there is some problem with this. Yeah. So earlier, okay, this page we lost somewhere. So on this page we had written this I T, it will depend on the two factors that are A1, AI, and the other one is tau. Okay. Okay, I do not multiply them because this is misleading. But IT will depend on the AI and tau. Now, if you want to calculate the relative contribution, what do you do? Simply is just consider AI and tau, and take just take the product. Okay. And okay, now if you want to calculate the relative contribution of A, in this case the first will be zero point 0.2 and it is say 1. So you can say simply the product will be zero point 0.2, And if in case of b, a2 the is 0.3 and tau is 5, so it will be 1.5. So if I just ask you what will be the relative contribution of each, so and so it would be b's contribution is greater than the contribution of a. Okay, so just go back to this question. When you go back to this question, here it is a tri-exponential function where the parameters are given to you, a1 and tau1, a2 and tau2, a3 and tau3. Okay, so if a1, if you want to calculate the relative contribution of a, so yeah, so relative contribution of a. So here amplitude is 0.5 and tau is, average lifetime is, I think it was zero point 0.4 if I'm not wrong. Okay, so we'll just try to write all the things all together, 0.1, 4 and 1 and zero point 0.1 and 6. Yeah. So the other is the relative contribution of B will depend on first A1 amplitude, or you can say A2. This is A1 and this is tau 1. So A2 is 0.4 and tau is 1.0. Let's just check. Yeah. And relative contribution of C will be A3 and tau. So it will be zero point 0.1 and tau 3, its value is 6.0. Now, the relative contribution, if you calculate for this, it will IT will depend on A1 and tau. So let's say this is zero point 0.5 into zero point 0.4. So it will come to be 0.20. Then the relative contribution from B will be zero point 0.4 into 1.0. So it will be zero point 0.4 into 1 is zero point 0.4. The other is A3, so it will be zero point 0.1 into 6.0. Yeah. Adrija, you can speak.
Sorry, mistakenly I raised my hand.
Actually, I think okay. Yeah. Is something wrong?
No, 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 nothing.
Yeah, so zero point 0.1 into 6 will again be zero point 0.6. Okay. So, okay, now actually in the question they are named as P, it is as Q, oh sorry, it is as Q, and this is as R. So, if you just take that the relative intensity for this will depend on zero point 0.6, say zero point 0.4 or zero point 0.1. So, for the first function, the contribution is least. For the second function, the contribution is a bit more, and what for the third function, it is zero point 0.6. So the total will be sorry, the order which we come which we come to know is the relative contribution to the intensity will be for R it is the maximum, then it is for Q, and then it is for P. Okay, so here we get the answer. R is greater than Q is greater than P. Okay. Yeah. So if you okay, now since I solved this question, I think that I should give you another question which is similar to this, and you just try to solve it. Okay. So here I'm just writing the values, and I'll draw two more columns. Okay. So here I'll give A4 and tau 4 value. And suppose I give the value here 0.2, and this will be 0.8, this will be 0.9, and this will be 1.2, this will be, and this will be 0.4, and this will be 0.8, and this will be 0.3, and this will be 0.3. Okay, yeah. Okay, I'll write it to be 3. So okay, I'll just correct it. Okay, yeah. So this will be 3.2, and now you just try to calculate it.
So Q is the greatest.
Which one? Okay.
Q.
So I had not named the last one, so I have named it as S. So now you just tell me the order.
Yeah, Q will Q, then a Q greater than S, greater than R, greater than P.
Okay. So since you have solved, I'll also just try to solve it in short. So first of all, for P, it will be 0.2 into 0.8, so it will come to be 0.16. Then okay, for the second Q component, it will be 0.8 into 1.2. Sorry, 0.9 into 1.2. 0.9 is 108, so it will be 1.08. Is it correct?
Yeah,
For the third one, it will be 3 into tau 3, it will be 0.4 into 0.8. So it will be 0.32. And the fourth one will be 0.3 into 3.0. So it will be 0.9. Right now? Or wrong?
it is right.
Yeah, okay. So then the order will be Q is greater than uh, S is greater than R is greater than P. Okay. So now my answer is also come to be the same. So definitely your answer is also correct. Okay. So thank you so much for solving. The other is data model that may be appropriate in system containing several fluorophores is. First is single exponential decay, staged exponential decay, multi exponential decay, and distribution of lifetimes. So first of all, uh, I'll just tell you one thing. For the single exponential decay, what we learned was, for a single exponential decay, uh, yeah, for a single exponential decay, let's say this is the plot of log of intensity versus time. So when you just take the plot, the decay would be like, you will okay, sorry, you will get a single straight line, okay, along the x-axis. So this will be your line. And if you remember what we saw in the lectures, like it, if there is suppose you, instead of this line you have some line which goes like this and then goes straight, then you do not consider this to be a good fitting at all. Okay, there is some factor which you need to change so that you get a good fit. Now, here what they asked is data model which is appropriate for system containing several fluorophores. So for several fluorophores, single exponential decay would not be. So the model that is fit is the multi-exponential decay. So how do you come to that, or how do you distinguish? Like, this is just an extra point. So if suppose you just take, construct a plot of log of intensity and time, and you do not get a straight line, that means you have to consider that your decay is of multi exponential, means there are other factors also which are governing multi exponential fluorescence decay, then it would be considered. Okay, now, and the one we talked about this in the previous question is also a tri-exponential decay, which we are solving, which through which we have, which is a data model through which we are able to calculate the intensity. Now there is another thing that is, okay, for one component single exponential is okay. For multi exponential, we need, for several fluorophores case, we'll need a multi exponential decay data model. But there is some other thing, that is distribution of lifetimes. Okay, so for that the intensity is given as, for that intensity is given as it, okay, yeah, here I'll write it is equals to summation of alpha of different lifetimes, that is distribution of lifetime, into e to the power minus t by tau deta. Okay, so this is the expression that is for the distribution of lifetimes thing. And if you want to determine, sorry, uh, if you want to determine the distribution, sorry, if you want to an appropriate model, so these two, multi exponential and distribution of lifetime, these two will be the right option. Okay, now, there since we have some more time left of about half an hour, I'll like to give you more questions regarding the same, like the some more numericals related questions. So first is the horizontal beam of pulse laser light that is reflected by a retroreflector in order to bring about a delay of 10 femtoseconds in the reflected beam. Okay, so in the retroreflector has to be moved by. Now, say I have, this is the delay of femtoseconds, and we had solved a question similar to this. Okay, and I had made you solve this question. Just help me if I just take the time to be 30 femto. Okay, sorry, I have not written on the right place. If I take the time to be 30 femtoseconds, how much the retroreflector has to be moved? Just try to solve the question, and if you are facing problem, I'll just help you, like I'll try to explain this point again. Okay, so while solving this question only, I'll try to repeat what I said earlier. Okay, so this is the case when we were studying the about the inner fluorescence. If as a source of light you take a pulse laser light and you have a retroreflector, like your light passes through this. Here is your first mirror, it gets reflected here. Here is second mirror, and this way it goes. So where did we use this thing? This thing we used when there was a sample, like this was your sample, and that was a pump probe technique which we called. So here you passed on this. So first of all, the sample you illuminated it with first range of light, that is called pulsed probe light. Okay, sorry, pulsed pump light, and the second one was pulsed probe light. Okay, I'll just make it sure. Yeah. So the first one was pulsed pump light, and this one was pulsed probe light. Okay. Now what we did was, first we illuminated our sample with this pulsed pump light initially, the one with this arrow. Okay. And now I'll try to change the color of this pen. Yeah. So this is the pulse probe light. So initially what we did, we illuminated the sample from ground with a pulse light. So it reached from ground state to the excited state. Okay. Now when immediately if we pass the pulsed probe light through this sample, what happens is, the through this we what the most of the absorbance will be from the excited state. Okay. And this absorbance, the population of this excited state will directly decide the intensity of the excited state. Okay. Sorry, the intensity of absorbance by this excited state. And that is how we know that, or we can relate with the population of this excited state. Now suppose this happened at 0 seconds. Why? Because there is no time lag. Immediately I illuminated it, excited it, and immediately I passed a pump probe light through this. Now after say 1 picosecond, again what happened? After, no, I did not illuminate it at 0 second. I illuminated it after 1 picosecond, or say one, yeah, 1 picosecond would be better. So but some of the population would have reached to some like ground state, and like the fluorescence decay would be happening now. So the now the intensity will reduce to this state. Why is this happening? Why is this decrease in intensity happening? Because some of my population is already decayed. Now the population of excited state is less, so intensity of the absorption is still less. Now if you take it after more time intervals with a more time lag, slowly you will get a graph like this. Okay. And this is the population or this is, because of this intensity you are able to calculate, or you are able to know, like this type of curve, what is the intensity or what is the population of the excited state at time 0. Now this 10 femtosecond delay, what is it? This is what I was talking here, 1 picosecond, 2 picosecond. Here we are considering femtosecond. Okay. So now earlier, what I told, if you want a delay of 10 femtoseconds, so you have to move this retro reflector to somewhat space, so that your this probe light, this pulse probe light, you can delay it a bit. There would be some time lag between this incident of this pulse pump light and incident of this pulse probe light. So first was 10 femtosecond. Now I have given you the value of 30 femtosecond. This did you solve the question?
Yeah, I solved.
Okay,
It is
wait
coming as
just a second. Yeah.
the distance is coming as 9 micrometer.
Okay, let me check if you have solved it correctly. Yeah. So first, um, how did you do? First, you would have taken the it as speed of light, okay?
Yeah,
Because earlier I taught you to take the speed of light in say 3 into 10 to the power 8, or more precisely it will be 2.99 meter per second. Okay. Now the time which I had given you was how much? Time of
30 femtosecond.
delay was of how much? 30 femtosecond.
30,
So it will be of 30 femtoseconds. Yeah. So first of all, yeah. So we solved it using a simple relation, right? Distance is equals to speed into time, right? So 3 into 10 to the power 8. Okay. Take distance is equals to 3 into 10 to the power 8 into 30 into 10 to the power minus 15 or 14.
50.
Yeah. So into meter per second. Yeah. So second to second will be cancelled, and so what will be left with it is 3 into 3 30 90 into 10 to the power minus 7. Is it right? Yeah. Is it right?
Yeah, it's
Yeah. So it will be 9 into 10 to the power minus 6. Okay. Now 9 into 10 to the power minus 6, what will be? It will be in meter, and it will be written as 9 micrometer. But so what was your answer, Adrija?
yeah, it was 9 micrometer only.
Yeah, but actually what I told you initially was that you have to do it because you have to take this entire time. So that's why you will do the, like, we have to move it with by half a distance of this. So our answer will not be 9 micrometer, it will be 4.5 micrometer. Okay, just half of it. Got the answer?
Yeah,
Now suppose I give you like this is another, or I'm giving you the inverse question. Suppose I give you that there is a delay of sorry, okay, I'll give you a question where there is some, what say, 20, oh no, 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 okay, we can say 20 femtos, no, no, okay, just a second, I'll frame a question where I'll say that suppose you have shifted or you have moved the retro reflector by say 3 micrometer, yeah, 3 micrometer. So can you just tell me how much delay in the signal will be, in the reflected beam will be? Yeah, so if you want me to write it, I'll just write that now I'm giving that I have moved the retro reflector by 3 micrometer. Okay, so what you have to calculate is,
femtosecond.
How much?
20 femtosecond.
Yeah. Okay. Okay. So wait, we'll just solve it together also. Yeah. So what I had given the question is 3 micrometer. We have shifted the retro reflector. Then how much will be the delay? Yeah, this is was the question. Now we have given distance, speed, and time. So speed into time was the answer. So distance, what I told you, you have to double the distance. So 3 into 2, it will be 6 into 10 to the power minus 6 meter. Is it right? Did you do the same?
Yeah, I also did the same.
Yeah, then we had taken the speed of light 3 into 10 to the power 8 meter per second. Okay, and now simply we have to calculate the time, which will be in seconds what we'll get. Okay, since I have solved we'll cancel both the units, meter, and we'll be left with. So it will come to the LHS. So it will be 6 into 10 to the power minus 6 upon 3 into 10 to the power 8 is equals to dash seconds. Okay, now if it will come to be 2 and this will go to, it will be 2 into 10 to the power minus 14 seconds. Okay, and therefore you can write it as 20 femtoseconds. Now I suppose that if this question comes to you anywhere in the exam, you will be able to solve this question in any way whatever they ask. Do you have any problem with this?
No.
Okay, then it's good. Now, I'll give you one more question which will be related to this experiment. Okay, so now, just a second. Suppose I give you there are 4,000 channels. Okay, and you are given a time of same 50 nanoseconds. Okay, so the tag range is 50 nanoseconds, but now you have only 4,000 channels in the MCA. So, what will be the temporal resolution of the experiment?
Twelve point five picosecond per channel.
Okay, and suppose I ask you to convert it to nanoseconds, or then what it will be? Yeah. So, I suppose you have solved it like 50 nanosecond per 4,000, as I told you. So it will come to be okay, and it will be 1 upon 80, right? Hello, Adrija.
Yeah.
So, 1.10.
Uh,
Yeah, is it right?
yeah.
So it will be okay, from nanoseconds to, so it will be 12.5 picoseconds, right?
Yeah.
Okay. Okay, so then our answer is correct. Now, related to previous live session, I think there was one question which we could not solve, right? Do you remember?
Yeah,
That was related to the emission quantum yield. So, I would
yeah.
like to cover that thing. Now, suppose I have given you, okay. Now, suppose there, I'll take an empty page. Yeah. So, here, yeah. So here I'll give you a question where we had done this thing. Suppose first of all I have given you, if I am not telling you any formula, earlier you have to calculate fluorescence emission quantum yield if the intensity of original intensity sorry intensity of absorption is say 40%. So, can you solve this question with only single value?
Maybe we require the intensity of emission.
Yeah. So, suppose I have given you that the phi is the emission quantum yield. So, what will be the formula? A formula would be intensity of emitted light upon intensity of absorbed light. Isn't it right?
Yeah,
Did I tell you the same in previous session?
yeah, of course.
Now, what we had just taken that since from the equation of absorbance we had taken as absorbance is equals to log of I naught by I, right? Then we had taken a log of I naught by I naught minus IT. Okay, sorry, I abs, I absorbed, right? Because this was the intensity of transmitted light. And then what expression we had come to? We had come to like 10 to the power a is equals to I naught upon I naught minus I absorbed. And then we had come to an expression that 1 minus, sorry, 10 to the power minus a is equals to 1 minus I absorbed upon I naught. Got it? Was this the right expression?
Yeah,
No, 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 no. And then if you take this entire thing, it will be like I absorbed is equals to I naught into 1 minus 10 to the power minus a. Now suppose if I given you the value of I naught and a, so then okay, I have given you the value of I absorbed. Now you have to calculate the value of I emission. Okay. So this question will not be that easy. Now I'll not give you the value of I absorbance. I'll give you the value of only absorbance. Okay. Then you have to calculate. Suppose the uh, I emission. Okay. Suppose the fluorescence quantum yield phi emission I give you to be 0.15. Okay. Just see, look at what are the things I'm just providing you the data. Okay, so phi emission I have already given you. I naught you consider to be 100, okay? And I emission you have to calculate if the absorbance is um, say 0.2. Just try to calculate once. I'll also try to calculate. Hello?
Yeah, I'm trying.
Okay. Adrija, can you turn your mic off?
Yeah. Intensity of absorption is coming as 37.
Wait a second. Wait a second. Okay. Yeah, so that is correct.
And intensity of emission is coming as 5.55.
Okay, so what there was the value of phi? It was 0.15, and then I emission was unknown, and it was 100 minus 100 into 1 minus, I think that is 0.63, so it has come to, yeah. Okay, so for the other viewers who may just look at this session afterwards, on a clear page, I'll try to solve this question because earlier in the last session we could like the time was also over, so we could not solve this question. Yeah. So now, could you solve the question and is your that doubt clear?
Yeah, it is clear.
Yeah. So from all the expressions we had what we had derived is, so these are all the other not unnecessary things. So first we'll write the, yeah. So in this question, this thing I had given you, that was intensity of light. So these were the options. I naught was 100, phi em or the emission quantum yield was 0.15, and the absorbance was 0.2. So we had to calculate what was the thing. I absorption okay, I emission okay. So first intensity of absorbed light also we could not get, and intensity of emitted light. So basically whatever we want in this formula, both the things we did not have. So the other formula which we had is the emission quantum yield can also be given by intensity of emitted light whole upon I naught, which is the intensity of the incident light, into 1 minus 10 to the power minus a. Is it right, Adrija?
Yeah, it's right.
Yeah. Now, see, this emission quantum yield was given to you. That was 0.15. Okay. It was equal to intensity of the emitted light, which was unknown. And I naught, what was it? It was 100. Okay. And then the other thing that was given to you was 1 minus 10 to the power minus A. And here A was also given to you. That was zero point 0.2. Okay. So now first we'll go from the initial. This is looking like an I, but this is not I, this is 1. So first of all we'll solve with this, we'll calculate the value of this. So it is 0.15 is equals to I emission whole upon 100 into 1 minus 10 to the, okay, so the value of this comes to be, the value of this comes to be 0.37. Okay. Now, oh, okay, sorry, the value of this comes to be 0.63095. Yeah, so it, the value of this come to be 0.63. Okay, or you can say 9. Now when you calculate this, IEM upon 100 into, then what comes to be 1 minus 0.63, it comes to be 0.37, and then equals to 0.15, and then IEM is equals to 0.15 into 37, right? And when you do this, what does your answer come? At, at,
0.55.
sorry.
5.55.
Okay, wait a second. 5.55, exactly. Got it? So then, huh. So then, now, like now, see, intensity of emitted light also you could calculate. And in all, we had one more relation which we could get was I absorbed is equals to I naught into 1 minus 10 to the power minus A. Using the same relation, we had this relation only we had substituted or at this place. So then I absorb also comes to be like 100 into 1 minus 10 to the power minus A. So this comes to be 37%. Now what we got to know is I absorbed was 37% and I emitted was still less than that, that was 5.755 only. So the conclusion is, if your system is like, if you have a sample which absorb only, like it can say x by 5 portion of light, what it emits will be around x by 12. Okay. Or actually this is not the real value, I'm just telling about the idea how much there is decrease in the intensity. So that is why earlier in this question, what we had studied was, why do we use the xenon lamp as the light source? Why? Because this was the lamp source which really produces highly intense light. And if you use the intense light of such high intensity, then only you will get a good intensity of emission light, and consecutively you will get a good quantum yield. And that like that your data, and then your data would be like one which could have a certain value. Okay. So now these are the questions which we had discussed. If you have any doubt in any of these, just ask me. We have some more time of 2 minutes. So is everything clear to you?
Yeah, everything is clear.
So okay. We'll end our session with this. So thank you so much, Adrija, for joining and
Thank you.
solving so many questions.
Yeah, thank you.
Yeah. So I'm just ending the session. Hmm.